Welcome back to NET Physics series. Today, let's solve some of the past paper questions from the chapter of light for NET. Let's start with question number 1, which reads that the condition for the constructive interference of two coherent beams is obtained when the path difference will be. So we have some options: integral multiple of lambda by 2, even integral multiple of lambda, integral multiple of lambda, odd integral multiple of lambda by 2. But remember, they're talking about constructive interference, and we know that the condition for constructive interference is n times lambda equals d hkl sine theta. Clearly you can see that when this is the case, we'll have constructive interference, and this implies that we have n times lambda. Now this n over here is just belongs to a family of integers, right? It belongs to a family of integers, which means that it can take any values 1, 2, 3, 4 and so on, right? Which means that it would be an integral multiple of lambda. So that's the correct option. All right, so let's move on to question number 2. Question number 2 reads, the index of refraction of diamond is 2.0. So the index, which may be represented with eta, is given as 2.0. It's a unitless number. Velocity of light in diamond in centimeters per second is approximately. So we are given the refractive index for diamond, and we are asked about the velocity of light in diamond. So we know that the refractive index, an expression for refractive index is the ratio of speed of light to the velocity of light in whatever medium are we talking about. So here the medium is diamond and the refractive index is for diamond. So rearrange this expression for velocity for diamond, and this becomes speed of light divided by the refractive index for diamond. Now just put the values. Remember, you have to use the value for speed of light in centimeters per second, which is approximately 3.0 into 10 raised to power 10 centimeters per second, and the refractive index is given as 2.0, which is a dimensionless number. So now we'll just do the math. So we know that this would give me 1.5, right? So if I divide 3 by 2, I get 1.5, and into 10 raised to power 10 centimeters per second. So that's the correct option in centimeters per second, which is this one, right? This is 10. So this is option D. Now let's move on to question number 3, which reads that position of the mth dark band would be written as. Now remember, when we saw the same thing in the theory part, we saw that if I have a double slit experiment, it would look something like this. And suppose that the distance between the screen and these fringes, these slits is, suppose it's L. And so on this thing, I'll see something like this, right? Which means that wherever I have this maximum amplitude, that's where I'll see bright fringes. And so the distance from this line, this center, this bright fringe to this bright fringe is given as y. Now, we know that the dark fringe would be given as a result of destructive interference, right? And so whenever we have destructive interference, that implies that our waves are out of phase. And so the path difference, I'll just use P dot D for path difference for these type of waves which are out of phase and producing a destructive interference. The path difference is given as 2n plus 1 times lambda by 2. Now this n is just any arbitrary variable. We can, even though we can call it m, right? It doesn't matter. So that is the path difference. And so if I relate this thing with the position of the mth dark fringe, then I can clearly see that this path difference times L, which is the length of the screen, length from the slits to the screen, and the gap between these slits, which is small d, I can write the position of the mth dark fringe as this thing, which is this path difference. So I'll just write it as path difference times the length of from the slit to the screen divided by the gap between these two slits, which is d, which becomes 2m plus 1 times lambda by 2 times L by d, which is this thing. So the correct option is D. All right, now let's move to the question number 4, which reads, two monochromatic waves of the same wavelength are traveling. So we have two monochromatic waves and they have same wavelength, both of them. They're traveling through a medium. So they're also traveling through one particular medium. They can interfere destructively provided their path difference is. So we have to again remember that the path difference for destructive interference is 2m plus 1 times lambda by 2. So if this is the path difference, then this thing 2m plus 1, this thing keeps in check that this value will be an odd value, right? And then we have lambda by 2, so half multiple of lambda, right? So this thing means that a cannot be the option because it, even though there is 1 times lambda, it's odd, but there is no half multiple with it, so that's not going to be the option. Then we have 2 lambda. This is clearly not an option because there is no lambda by 2 and there is no odd multiple with this, so that's not going to work as well. And the same reason for this as this one, because here we have an odd multiple but it's not half multiple, and so that's not the answer. Here you see 3 by 2, which means that m took the value of 1, which means that this thing became equal to 2 into 1 plus 1, which is 3, and lambda by 2, right? So 3 lambda by 2, which is this option, 3 lambda by 2. So correct option is option B. Alright, so now let's move on to question number 5, which reads that if a torch is used in place of monochromatic light in Young's experiment, what will happen? Fringe will occur as from monochromatic source, so that means that no difference will happen. No fringes will appear, implying that we'll not see any fringes on the screen. Fringe will appear for a moment and then it will disappear, or only bright fringes will appear. But note that in a torch, you'll only see from torch, you can say it's a source of white light. Now this white light will separate into colored fringes, right? When it separates out into different wavelengths of different colors. So you'll observe different colored fringes. Now these fringes which are observed, they will be blurred, or almost, you cannot be able to see these colored fringes because of overlapping of these waves, or you can say overlapping of these fringes, which means that you can clearly understand that this would be implying the fact that no fringes would be really appearing, because when you throw this torch in sub double slit experiment, then because of the fact that these fringes would be blurred, so in a nutshell you'll say that you cannot really see any fringes, and hence no fringes will appear. So moving to question number 6, if the distance between a point source and a screen is doubled, so the distance is doubled, then intensity of light in the screen will become what? Alright, so what do we know about intensity? We know that intensity obeys the inverse square law principle, which means that if I have something like this. Now if I am going to double this distance, then intensity should decrease 4 times, right? So if R goes to, you can say it is doubling, right? So it goes to 2R, then this square of R square would go to 4R squared, right? And then this thing would be that intensity is inversely proportional to 1 by, because R is doubling, right? So it is, you can say that intensity would be becoming 1 by 4, right? Because this thing would take this form as, let me write it like this, 1 over R squared would take the form of 1 over 4R squared, but I know that this thing is proportional to intensity, right? So 1 over 4 times, I can replace 1 over R squared by intensity. So this means that the intensity is going to 1 by 4. So it becomes 1/4 if I double the distance, which means that the correct option is option B. Alright, so with that we can move on to question number 7. And question number 7 states that the refractive index of water is 4 by 3. So we're given the refractive index for water, and that of glass is 5 by 3. So we're given the refractive indexes of both the mediums. What will be the critical angle for the ray of light entering water from the glass? So what do we know about critical angle and refractive indexes? We know that the refractive index, the ratio of the refractive index of two mediums, is defined as, so I can say the refractive index of glass over refractive index of water is defined as 1 over sine of the critical angle theta c. This means that because Ng, which is the refractive index of glass, which is 5 by 3, and for water it's 4 by 3, so 3 goes away and we are left with 5 by 4. So we can just get rid of it like this, and this is equal to 1 by sine theta c, which means that sine theta c is equal to 4 by 5, and so theta c is just the arc sine or sine inverse of 4 by 5, right? So arc sine is just sine inverse of 4 by 5. So that's option D, right? So that's the correct option for the theta c critical angle. All right, so let's move on to question number 8. And question number 8 reads, the white light is incident on the interference of glass and air as shown in the figure, right? So we can see that here we have, this is the white light, and here we have a glass placed like this, and on the opposite side of the glass it's just air. So you're throwing white light on a glass, and what's happening is that the green light is totally internally reflected. So it's internally reflected in the glass. It's completely internally reflected, so the green light, you can say, is kind of eliminated, and then the emerging ray in the air contains. So we want to see what would be contained in the air if the green light is totally internally reflected, which means that it is completely now inside the glass. So we have some options: all colors except green, violet, indigo, blue, all colors, yellow, orange, red. Alright, so let's think in terms of the critical angle, right? So we have theta c, which is basically, we saw, sine inverse of 1 over n. Now n, the refractive index, is inversely proportional to lambda. Now let's think about yellow, orange, and red. They have, we know this as a fact, that the wavelength of yellow, orange, and red colors is greater than the wavelength of the green light. So this means that the critical angle for these rays of light will be higher. Hence, if green is totally internally reflected, then the only lights that would be visible or that would emerge out would be the rays of yellow, orange, and red. So the correct option is option D. And so it cannot be violet, indigo, blue, and any other option, because the rest of the colors which we have, they have a wavelength which would be smaller than the wavelength of the green light, and so those will not be those rays will not emerge out, because the critical angle for those rays would be smaller, and so they would also kind of, be internally reflected due to the small critical angle. So next question is question 9. Which one type of fiber is more suitable for transmission of signals in which white light is used? Right? So we have different options: mono mode step index fiber, multi-mode graded index fiber, multi-mode step index fiber, single mode step index fiber. So the step index fiber is, for example, let me just try to draw this thing. Whenever you have a step index fiber, a single mode will just look like these waves. So they are just coming and bouncing back and being reflected like this. For multi-mode, you'll have more than one, right? So there'll be things like this, then you'll have this, and so this is the multi-mode. Now this is step. However, the graded index fiber, the multi-mode graded index fiber is the one in which I have one mode, single mode, something like this. So it's smooth. It's more smooth compared to the step one. And so if I draw multi-mode, then there will be more modes like this. So this is graded. So the more suitable type of fiber would be the one where we would have less dispersion, right? And clearly we can see that the dispersion of waves is less in this medium, which is the graded fiber, compared to the step 1. And in fact, even the difference between time, it would be smaller in this one, in the graded multi-graded fiber, compared to the step 1. So the correct option would be multi-mode graded index fiber, which is option B. So let's move on to question number 10, where we have, consider a ray of light traveling from a denser to a rarer medium. So something like this. If it is incident at the critical angle, what will happen then? So we have a ray of light and it enters like this, and then if I draw a normal to the point where it hits this, and if this is you can say if this is dense and this is rare, so let me actually then draw this ray of light a bit more closer to the normal, because in a denser medium the ray is, if it's closer to the normal, then in rarer medium it will divert away from the normal like this, right? Now if they're saying that if the incident is at a critical angle, so if the ray that is passing from the in the dense medium, it is moving in the denser medium, if the angle is equal to the critical angle, what will happen then? It will emerge out into the rarer medium, it will undergo total internal reflection, it will travel along the interface separating the two media, which is this thing, right? So it's saying that it will just travel along this thing, or it will retrace its path. So we know that if a ray is traveling from a denser medium to a rarer medium, and the angle of incidence, which is this one, so this is theta I, which is, if it's equal to the critical angle theta C, then the ray travels along this medium. So it will travel like this, which is the medium. So it will travel along the interface that separates the denser medium from the rarer medium. So it will look something like this. So the correct option would be B. They have labeled the options very weirdly. So it would be this one, which is it will travel along the interface separating the two media. Alright, so let's move on to the next question, question number 11. The distance traveled by the light between primary wavefront to the secondary wavefront is given by. So if I recall that if I have this as my primary wavefront, right, and there are some points on this wavefront from which these points, around these points we develop these secondary wavefronts, remember? So it's like this, like this, like this, something like this, right? And these would give a rise to the maximum point on these wavefronts to a new wavefront, something that would look something like this. Now they're asking you the distance which is traveled by light between these two wavefronts, right? So this one, which is the primary, and this one, which is the secondary. Now we know that the displacement or the distance is given by S is equal to V times T, where S is the displacement, V is the speed or velocity, and T is the time. Now because in this case light is traveling, so V is just the speed of light, so this equation becomes S equals CT, right? So this means T would be the difference in time really between these two waves being formed, primary and secondary. So I can say that this is just C delta T, where delta T is the time difference from at this point and at this point. So these 2 points, the difference between those 2 points. Hence, the displacement or the distance is given by S equals C delta T. So the correct option is option C, C times delta T. Let's move on to the next question, question number 12. When the light enters in a glass, there is no change in its velocity, frequency, wavelength, or direction. So we know, for example, if I have this thing and if this is a glass, right? And before the glass I have, let's just say we have air. And so if it's entering at this point, what happens is it will go like this and it will incident on this glass, and then it will kind of become closer to the normal because it's going from a rarer to the denser medium. So obviously you see that the direction is changing. So direction changes, right? Now direction is changing. We also know that v is velocity, right? And velocity also changes when it goes from a rarer to a denser medium or otherwise. So we know that light it slows down when it goes through a denser medium. So velocity is also going to change. Now we know velocity is equal to f lambda, where lambda is the wavelength, f is the frequency. Now lambda, because velocity will change, so lambda will also be changing. Wavelength of the light also changes in this case when it goes from a rarer to a denser or other way around. The wavelength changes. What remains the same is the frequency, which is f equals to 1 over time period. Time period is going to be constant. This is constant, and which implies that the frequency would be constant. There would be no change in the frequency. Hence the correct option is option B, because it says when the light enters in the glass, there is no change in its frequency. Moving on to question 13, maxima is termed as, it's a very simple question, bright fringe, white light, monochromatic light, dark fringe. We know maxima is where we have maximum or constructive interference, right? Constructive interference. So that is where you see bright fringes. So the correct option is option A. Then let's move on to the next question, 14. It's a bit unclear, but I'll read it out. So when a two-slit arrangement was set up to produce interference fringes on a screen using a monochromatic source of green light, so you're using a monochromatic source of green light, the fringes were found to be too close together for a convenient observation. So the fringes were so close that you could not really observe them properly. In which of the following ways would it be possible to increase the separation of the fringes? How can I increase the distance between these fringes? So if you remember, we know that the fringe width is given by lambda times, which is the wavelength, times the distance from the slits to the screen divided by small d, which is the gap in the slits. So the options are decrease the distance between screen and slits. If I decrease this d, then fringe width would decrease, which would basically decrease the separation even more. But we don't want that. We want to increase the separation. So that's not going to work. Then we have increase the distance between the source and the slit. Again, this is not going to work as well, right? Because if you're increasing the distance between the source and the slits, you're really increasing d again. So that's not working. Have larger distance between the two slits. So if I increase this small d, then the fringe width would again become smaller because it's inversely proportional to this. So that's not going to work. Replace the light source with a monochromatic source of light. Now that's going to work because the wavelength of red light is greater than the wavelength of the green light, which means that this thing would increase, and so the fringe width would increase, right? So that's the correct option, option D.